All right, boys. Hope you're doing well. We worked through most of this problem today, and I want to finish it up now for your viewing pleasure. So, we've been dealing with volume problems, right? And we're thinking about volume of any solid, really, as the accumulation or the stacking or the building or the integration of the areas of all of those two-dimensional cross sections. Okay. Now, as long as we know the area formula for those cross sections, then we can build or stack or integrate or accumulate all of those areas and therefore get the resulting solid volume. Okay. So all we're doing is building, stacking an infinite number of circles or an infinite number of triangles or rectangles or squares, as long as we can come up with and articulate the area, as long as the area is known for that cross section, then we can find the resulting volume of that solid. Okay? So we worked through part A today in class, we worked through part B today in class. Let's take a look at part C. Okay? Now part C is a little curious because C, we know the R is the base of the solid, which means R, this area in here, the area betwixt those two curves, R is the footprint of a solid. So we're not rotating anything. Okay? From that footprint, we're going to create squares, and these squares are going to be vertical, perpendicular to the x-axis, coming out at us. So if I were to draw a couple of those square cross sections, that might be one of them. This might be another one. Okay, this might be another one. Okay, so all of those squares are kind of coming out at us into our faces, popping out of the screen, coming to life. Okay, so those squares now determine of course, what the cross sections are. So for this particular problem, part C, I'm going to integrate from 0 to 2. Okay, that's not changing. The areas of all those square cross sections, right? And of course, the area of a squared is pretty simply the side squared. Okay, so a square has a known area, so therefore if we integrate all the areas of those infinite number of squares that we're stacking from 0 to 2 along the footprint of R, then we're going to create a solid, right? There's no rotation, there's no circles, so to speak. Okay. So now I just have to kind of think about, well, what the heck are each of those sides going to be? Okay. And so for each of the sides, I can just draw one right now. Maybe I'll kind of in green, or maybe I'll outline a couple of those sides. Okay, each of those green pieces are the sides, right? In fact, the side, and they're all the same of a square for each individual square. Each of those sides can be articulated using the two functions f and g. Here's how we're going to think about it. Okay, this whole length here, if I kind of work from the x-axis all the way up to the top function. Now remember, the top function is the cosine. Maybe I'll remind myself that the top function is g and the bottom function is f. Right? But if I think about this whole length, right, would be the output of g. Okay, so from this whole length that I'm outlining on my screen right now, hopefully you can see that green dot moving up and down. If that whole length is g, I just want to subtract from that to get the side, f, which would be this piece. Right? The whole length would be g, the y output of g, the y value of g, which is g. And from that, I want to subtract f. Right? So each of the sides in this case is going to be my upper function minus the lower function. That's how I create each of those sides. So therefore, when I integrate the side squared with respect to x from 0 to 2, I will get the volume of this resulting solid. Okay, and I'm just going to leave it like that. I don't need to put my cosines and then 2x squareds back in. But we can see how we're building volumes with any known two-dimensional area of a cross section. In this case, they're squares, and we're just going to build those. We're going to stack those. We're going to accumulate all those infinite number of square cross sections with R, the region between the curves, as our footprint from, in this case, 0 to 2. So therefore we integrate s, the side squared. Each of the sides is the top function minus the lower function. So we integrate the top minus bottom squared with respect to x from 0 to 2. Now there's no pi, there's no circles, right? Circles come up with pi r squareds for the disk method, or pi big R squared minus pi little r squared for the washer method. Okay, but there's no circles, so therefore there's no pi in here. We're just integrating squares, right? Which we know have area of s squared. Okay, so this is another problem which I hope will add to our volume prowess. So we should now be able to integrate virtually any function or any volume. We should be able to find any volume by integrating the area of whatever the cross sections are, as long as we can articulate, or as long as we know the area of each of those infinite cross sections. All right, so I hope this video is helpful. I want you to finish up that work from class today. I'll see you guys tomorrow.